This is Fiza from Group 316. Today's topic is properties of materials. Stress strain relationship, the constitutive equations. If we take a rod of some materials and subject it to a load along its axis, we accept that it will change the length. We might draw a load by displacement curve based on the experimental data. This is it. We could construct a curve like this for any rod, but it is obvious that it is dependent on the geometry of the rod as much as on any property of the material from which is made. We could, however, chop the rod up into a smaller element and apart from difficulties close to the end by the same amount. The shape of the stress and strain curve illustrated in figure is typically of many engineering materials and particularly of metals and alloys. In the context of biomechanics, it is also characteristic of bone, which is studied in more details in a section. There is a linear portion between the origin O and point Y. In this region, the stress is proportional to the strain. The constant of proportionality E is Young's modulus. Materials like rubber we stretch to high strain tends to follow very difficult loading and unloading curves. A typical example of an axial test of a rubber specimen is illustrated in the figure. This phenomenon is known as hysteresis, and the area between the loading and unloading curve is a measure of the energy lost during the process. Over a period of time, the rubber tends to creep back to the original length, but the capacity of the system as a shock absorber is apparent. This is the graph which explains the typical experimental and uniaxial stress strain curve of rubber. The concept of homogeneity and isotropy are of particularly important to us when we begin a study of biological materials. A homogeneous material is one of that is the same at all points in space. Most biological materials are made up of several different materials, and if we look at one point in a piece of tissue, we might that they are not the same at all points. For example, if we look at one point in a piece of tissue, we might find collagen, elastin, and cellular materials that material in a homogeneous. Isotropic material is one that exhibits the same properties in all directions at a given point in space. Many composite materials are deliberately designed to be anisotropic. For example, a long bone will have fiber originated along the axis, and pressurized tube will have the fiber running around the circumferences. Despite the problem outlined above, simple uniaxial stress strain tests do provide a sound basic for comparison of the mechanical properties of the materials. Typical stress strain curve can be constructed to describe the mechanical performances of many biomaterials. Bone. Bone is a composite material containing both organic components. The organic components above one third of the bone mass include to the cell osteoblast and osteocytes and osteoids. The inorganic components are hydroxylated and material salts, primarily calcium phosphates. The osteoid contains collagen of the fibrous protein found in all connective tissues. The material salts give the bone in a hard and in compressive stiffness and strength. The stiffness of the salt crystals in a above 150 GPa, approaching that the steel. The skeleton in is composed of cortical, compact, and a spongious bone. The distinction between made based on the prosperity and density of the bone material. Cortical bone is found where the stress are high and cancellous bone where the stress are lower because the load are more distributed but high distributed stiffness is required. The aircraft designed use honeycomb cores in situations that are similar to those where cancellous bone is found. Properties of chorioidal bone: hard and has a stress strain relationship similar to many engineering materials. Anisotropic, meaning its property depends on the orientation of the load relative to a collagen fiber. Strongest in a compression, weaker in tension, and weakest in shear. Strength and stiffness vary with age, sex, strain rate, and whether it is wet or dry. Comparison with steel. Chorital bone is approximately one tenth as stiff and one-fifth as strong as steel. Unique features of living bone: remodel itself in response to stress acting upon it. This process is known as Wolff's law. Tissue. Tissue is a fiber of a human body. Types of tissue. Four basic types of tissues: epithelial tissue, connective tissue, muscle nerves. And connective tissue includes tendon, ligament, bone, and cartilage. Connective tissue. Connective tissue supports and connects other tissues and organs. Tendon connects muscles to bone or other muscles. Ligament connect bone to bone at joints. Composition of soft tissue. Soft tissue is a composite material made up of cells and intracellular material. Intracellular material includes collagen, elastin, reticulin, and ground substance. Proportion of material varies depending on tissue type. Collagen fiber. Collagen fiber are the most important components of the soft tissue for mechanical properties. Properties of tissue governed by amount of orientation of the collagen fiber. Fiber can be parallel, curved, or spiral, affecting tissue behavior. Tissue behavior underloaded. Tissue behavior underloaded is complex and not fully understood. No satisfactory first principle explanation of the experimental data. Properties can be measured and constitutive equations developed to fit experimental observations. Stress strain curves. Stress strain curves of collagenous tissue exhibited a characteristic shape. Tissue include tendon, skin, resting skeleton muscle, and scleral wall of the eye. Viscosity, viscoelasticity. Viscoelasticity refers to the dependence of a stress and strain on the time and rate of the loading. Some tissues exhibits the viscoelasticity behavior while others do not. Models of viscoelasticity. Viscoelastic model describes the behavior of a material that exhibits both elastic and visco properties. These models are based on the assumption that a rod of viscoelastic materials behave as a set of linear springs and viscous dampers in a some combination. Basics building blocks of viscoelastic models. Linear spring presentation that elastic properties of the material. Viscous dampers represents the viscous properties of the material. The combination of spring and dampers can be used to model the viscoelastic behavior of a tissue. Importance of viscoelastic models. Viscoelastic models are important for understanding the behavior of tissue under the different loading conditions. These models can be used to predict the response of tissue to various types of loading including static and dynamic loading. Behavior under constant load and displacement. First, Maxwell model force relaxes exponentially and asymptomatic to zero. Wittig model requires an impulse to obtain displacement and force in constant thereafter. Kelvin model initial force is required to displace spring elements and force relaxes as the Maxwell elements relax. Value of viscous elastic model. Models helps understand observes performances of viscoelastic materials. Most soft biological tissue exhibits viscoelastic properties. Thank you.